Hey guys, so this is going to be the third video for chapter 10. So section 10.3 is addressing the learning objectives number 6, 7, 8, and 9. So there's four here as well. So we're going to talk about how to define and some examples of the pre-post designs, how to identify threats to internal validity for those pre-post designs. We're going to describe the non-experimental pre-test, post-test design and the quasi-experimental time series designs and some examples of those. And then we're going to talk about how you get to that quasi-experimental time series design by just replacing the single observational or the single observation before and after the treatment with multiple or a series of observations to kind of affect that internal validity component. So this section is really focused on the second general category of non-experimental and quasi-experimental designs. So we talked about in 10.2, the one that kind of mirrors a between subjects design, the non-equivalent group designs and the things that go along with that. But now we're going to talk about the within subjects kind of aspect of non-experimental and quasi-experimental. And these are those pre-post designs. And so remember, these are talking about a series of observations made over time, and that's why it's within subjects. Think pre-post test kind of thing. But here, the difference between these and what we talked about last week is that, because we did talk a little bit about pre-post last week, but the difference there, the reason those were non-equivalent group designs or considered more between subjects is because there's no control group in these designs. So it really is the same group of people being observed pre and post. There's no comparison between groups. There's no control group to compare where everyone is receiving the treatment. We're comparing all of them. Instead of focusing on comparing a control group and a treatment group, we're comparing the pre and post test scores for everybody. So that is the main difference for this section. So I've kind of already introduced the idea of it just from what I just said, but again, the pre-post designs is that one group, just one, there's not multiple groups, is measured before and after treatment. So pre-test, pre-test, treatment, and then post-test. And remember, treatment it doesn't necessarily mean clinical. I know that sounds clinical, but just like what we talked about in the experimental settings, the treatment can just be, it can be a manipulation, it can be a clinical intervention, it can be a class on something, it can be an anger management program, it can be, lots of different things. So it doesn't necessarily mean treatment like in a medical or a clinical setting. Although oftentimes it is. These designs are often used for that purpose. So because of that, because it's one group and they are being tested, over time, they're being tested more than once before and after treatment. The threats to internal validity here are the same as they were in chapter 9, are time-related threats. And remember, there's these 5 right here: history, instrumentation, testing effects, maturation, and statistical regression. Remember, those testing effects are the things like fatigue and practice, things like that. So we're not going to necessarily go over all of those again, but just remember, if you need to look back at chapter 9 to remind yourself of what those are the same kind of threats that you're going to have to be aware of in a pre-post non-experimental or quasi-experimental design. So there's 2 main kinds of pre-post designs that we're going to talk about. The first one is the non-experimental version, which is just simply a pre-test, post-test design, which is what we're going to talk about next. And then after that, we're going to talk about the quasi-experimental version, which is it's called a time series design, but we'll talk about that in a second. So the non-experimental is called pretest post-test. The simplest form here is literally just OXO. So remember we talked about in the last video that notation where the O is the observation, the X is the treatment, and then the other O would be the observation. So literally they're observed one time, they have some sort of treatment or you know, some kind of intervention, something changes, right? And then they're observed again post. So pre-test, treatment, post-test, right? That's the simplest form. There's no, because this is non-experimental, or the reason this is non-experimental is because there's no attempt to control all of the threats to internal validity. There's no attempts to control the history, instrumentation, testing effects, maturation, regression, any of that. Because in most cases, it's because they can't. Because of the structure of the variables, they can't, there's no counterbalancing, right? They can't counterbalance here. Because counterbalancing, remember, would mean that some of the participants would experience the things in a different order, but you can't do that here, right? Because you have to observe them before, then they have to have the treatment, and have to be observed after. There's no way to reorder things, right? And so because of that, it is considered non-experimental. We can't, make any effort to account for these internal validity threats. And so you can't make those definitive cause and effect conclusions. An example that they use in your book for this is assessing political attitudes or views on a candidate before and after they see a new ad or a commercial about that candidate. So, they are evaluated before, getting their opinions are, they're surveyed before, and then once they see the ad, then they're observed or surveyed or whatever, their opinions are collected after. And so that's the simplest pre-test, post-test design. Now, if you wanted to make it to where the internal validity threats are reduced a little bit, it would become quasi-experimental. And all you need to do, the simple modification you can make here to minimize those threats and produce a stronger design, a stronger research design, is to just, instead of observing them only one time before and after the treatment, you can observe them or take measurements multiple times. And so when you do that, that is called a time series design. So it is literally the reason it's called time series, it's literally a series of observations before the treatment, and then there's the treatment, and then after. So the visual version of this would be O, 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 X, O, O, O would be an example. It doesn't have to be 3 observations. It can be more, it can be less, but that's what is used many times is 3 observations before, and 2 or 3 observations before, and then 2 or 3 observations after the treatment. Now, an example that they give for this is in your book is they take the blood pressure of participants several times, maybe like the day before, the day of, and then right before the relaxation training. And then they take it immediately following the relaxation training. They take another reading before they leave work that day, and then they take another reading the next day of their blood pressure, and they can compare those. That's to see the effectiveness of this relaxation training. That would be an example of a time series design. The relaxation training is sort of a manipulation. It's not true manipulation, but it is something that you are introducing, right? If it's not something that you're introducing, if it's something that is just happening environmentally, like an earthquake, we'll talk about that example in a second, then it's called an interrupted time series design. So when the researcher doesn't have that control over the event or whatever the thing is that is considered your treatment, it would be considered an interrupted time series design. And the example they gave in your book is an earthquake. So they are comparing health scores or well-being scores before an earthquake and then after, maybe in the month leading up to, the week leading up to, the day leading up to this earthquake, and then the day after, the week after, the month after. And you can compare that to see how that earthquake affected their well-being. Now, you may have thought about this when I was just saying that. Well, now hold on. You don't know when an earthquake happens. So how are you supposed to get scores beforehand? In interrupted time series designs and in things where you don't know the event is going to happen in advance, then you have to rely on archival data, meaning you have to go back and look at their um, doctor health reports, whatever you're looking at, their vitals, things that are reported to their doctor or to whoever. You would have to go pull that information from before the earthquake, and then you would be able to measure them after the earthquake, or you could pull it, after as well. But again, in those situations, you're going to have to rely on data that was taken by somebody else. It's called archival data that has already been collected. Because again, you didn't know this earthquake was going to happen, and so if you're going to study that, you can't. Obviously, you can't go back in time and collect that data. So those are some examples of those two. The value of this, the way that this helps minimize the threat to internal validity here and produces a stronger design, is that this first point is showing you that it allows researchers to see existing trends in the data beforehand. So it doesn't say that, it doesn't say before, but I'm throwing that in there those pre-test observations. And you can see at the very bottom, it also allows researchers to observe post-treatment trends. But as far as the pre-test trends, or even looking at the post-test and pre-test trends together, you can identify practice effects, fatigue effects, maturation, all of those things. You could be able to notice those by comparing them. And so in your book, this figure 10.5 shows you how an example of how some kind of outside event, like a history effect, could affect your scores. So here, in part A, you see that those O's at the bottom are the observations, right? So between observation 2 and 3, something happened and it caused the scores to increase. Well, then the treatment occurred and the scores didn't ever change. So the treatment didn't have an effect according to this, but if you look, something happened to cause these scores to change. So if all you did was looked at observation 2 and 4, it may look like the treatment had an effect, but really there was something else that caused this jump in scores. And so doing these multiple observations like this shows you that it wasn't your treatment. In fact, it was something that happened before. B is the exact opposite, right? It's showing you that something happened after the treatment. And again, if you had just looked at observation 1 and 6, it would look like there was a jump in the scores and that the treatment was effective. But again, by doing those multiple observations, you can see that it was actually something else, and not the treatment. And then part C down at the bottom, this is when the outside event and the treatment occur at the same time. So between observations 3 and 4, the treatment occurred, but also something else occurred. And unfortunately, when that happens, there isn't a way to see if the treatment had an effect or it was that outside event. There's no way to tell. And so that is one of the reasons why you can't make definitive cause and effect explanations or descriptions from, or conclusions from this design, and why it is quasi-experimental, because in that situation, there would be no way to tease apart which one was the actual influence on the scores changing. And so that just kind of gives you an example of that. The example in your book for part C here. They talked about depression scores and a treatment for that. And so they measured their depression scores before, then there was a treatment, and they measured them after. And that treatment, when they started the day they started the treatment, the weather had been really gloomy, on the before observations. And then after several, days of gloomy weather, it was suddenly warm and sunny again the day they did their treatment, or the day they started their treatment, or whatever. And so there was no way for the researchers to know if that jump in scores, if that improvement in their depression scores was because the treatment was effective, or was it just because the weather was bright and sunny and everybody was just feeling better and in a better mood. So those are just, things, again, that you have to be aware of when looking at these designs. So this last bullet point talks about, it allows the researcher to observe post-treatment trends. And so a visual example of that is on this slide here. So you can see from this example here that if you just looked at observation 3 and 4, again, you would assume, if you were just doing a simple pre-test, post-test, so observation 3 is the pre-test, observation 4 is the post-test, the treatment's in between, it looks like there's an increase in the scores, and so the treatment's effective, right? But when you do those multiple observations, especially after the treatment, and you see that the scores are continuing to go up, that is showing you that something else is going on here. And if you look at the pre-test, that's also showing you that the scores were already headed up before the treatment, and then they continued to go up after the treatment. The treatment didn't actually change anything. It didn't cause a disruption in that trend that was already occurring. So something, another variable, was causing that increase there, causing that trend that has nothing to do with the treatment. And so using those multiple observations allows you to see that, right? If you only did 2 observations, one before and one after, you wouldn't have known that that trend or that pattern existed. So this last slide here of information is just telling you how, in some cases, these time series designs are often applied to single individuals or single organizations, like one high school or one client. And so if they are used in that way, if they're focused just on that single case, rather than a larger group of participants or a larger group of organizations or high schools or whatever, it is occasionally called a single case time series design, or just simply single case or single subject designs. And we will talk more about those kind of designs in chapter 14. So what we're talking about here is more in reference to those larger group of participants or organizations. So that is it for that. We're going to do our knowledge check real quick. How does the time series design reduce the threat of external events, those history effects? And so hopefully you know that external events can be a threat to internal validity in time series designs, but like we just talked about in that example, it's only if the event occurs exactly, simultaneously with the treatment. If it occurs at any other time other than when the treatment is administered, then you should be able to, it should be fairly easy to separate those history effects from the treatment effects. So it's reducing those threats to internal validity, because you should be able to see those effects easily through those multiple observations before or after the treatment. So really quickly, we're going to go to our learning check as well. So what design is being used by a researcher comparing depression scores before and after treatment in one group of clients? So obviously, since they're comparing before and after and not comparing groups, there's no control group here. It's not differential. That rules that out. And then the pretest, post-test, non-equivalent control group, it rolls that out as well. No control group. And then, or well, actually, I said that backwards. No control group. That's that one. Differential wouldn't even have a control group anyways. That would be not a pre and post test. Since it's before and after pre and post test, it's not differential anyway. And then The post-test non-equivalent control group obviously doesn't make sense either because there's no control group, but also it's not post-test only. They just said they're comparing before and after scores. So obviously this is a pre-post design. And then number two, which of the following is common in within subjects experimental designs, but is impossible with a pre-post design? So we're talking about experimental versus the pre-post non-experimental designs. And hopefully you know from our slides that we just discussed that you cannot counterbalance. So within subjects, experimental designs are counterbalanced to avoid those or minimize those internal validity threats. You cannot counterbalance a pre-post design. And so hopefully that you were able to gather that from the information that we discussed in our slides and from reading your textbook. Number three, a clinical psychologist measures body satisfaction for a group of clients diagnosed with anorexia each day for 1 week before and for 1 week after they begin therapy sessions. So what kind of design is being used? Well, obviously, it's not just one observation, so it's not pre-test, post-test, because there's multiple observations. And so that says time series. Obviously, equivalent time samples is not even something we talked about, so it's not that. So you have to decide if it's regular time series or interrupted time series. And hopefully you realized from looking at this that the interrupted time series, remember, is when it's an event outside of their control. But this is a therapy that is obviously being introduced, and so it is not considered interrupted. It would be considered just regular time series design. And then number four, what can a researcher determine by using a series of observations before treatment? So that's the diagrams that we were just looking at, the graphs that we were just talking about. By seeing those series of observations before, you were able to see if the scores are influenced by some factor that's unrelated to the treatment. Obviously, that third answer, influenced by individual differences, that doesn't even apply to this design because we're not talking about between groups. And then the treatment having a temporary effect or a permanent effect, that would be things you would be able to observe post-test. But the question is about observations before the treatment, pre-test. And so that would be that last answer, that you can see if there's some other kind of history, maturation, some other kind of effect going on before the treatment. So hopefully that helps you guys. And if you have any questions about 10.3, let me know.